Hello again. Today we're going to finish our discussion of polar functions by talking about the area between two polar functions. So let's get started. There's two cases we need to consider. The first case is where we're talking about the area outside of one of the polar curves that's on the graph, but inside another one. Okay? So we know that this is the formula for the area inside of a polar curve. We talked about that in the last video when we were just talking about one polar function at a time, but now we've got two on the same graph. So if I want the area outside of one function and inside of another, I'm going to call the outer function capital R of theta and the inner function little r of theta, so that the area outside of the inner function, but inside the outer function, is going to be 1/2 times the integral of capital R squared minus 1/2 times the integral of little r squared. And if I want to just make my life easier, I can factor out the 1/2 out of both and put them in the same integral. But I have to remember to square the functions first before I subtract them. All right, so here's an example. I want the area that is outside of the function r equals 1, and that's the red circle, but inside the function r equals 2 times the cosine of theta, and that's the kind of blue one there. So that's the area that I want. So how do I find that? I don't need to calculate the area all the way from 0 to 2 pi because the area isn't covered by that many values of theta. So I just need to figure out where the area actually starts according to theta and where it actually stops according to theta, the angle. So let's figure out the area where the two functions cross. How I do that, I set capital R equal to little r, and I solve. So 1 equals 2 times the cosine of theta. Theta is going to equal negative pi over 3 or pi over 3, and if I draw those on the graph, I can see that that's where the two functions cross. It's also where the area starts and stops. So I'm going to let alpha equal negative pi over 3, that's my starting angle, and beta is going to equal pi over 3, that's my ending angle for my integral. So there's the generic formula that I talked about in the last slide. I'm going to plug in what I know. So it's going to be 1/2 times the integral from negative pi over 3 to positive pi over 3 of 2 cosine theta squared minus 1 squared. And so I go to my calculator again and I figure out what that is. That is about 1.913. Okay, so that's an example of the first case. The second case is where I want to find out the area that is common to both curves, so the overlap of both functions. To do this, I need 4 angles, not just 2. I need to figure out where each of the angles starts and stops being a boundary of my area. Okay, so for the first curve and for the second curve. So one of the curves is going to start at theta 1, which is just what I'm going to call it. And if I follow theta around and I see where one function stops being the boundary and the second function takes over, I'm going to call that theta 2. And I'm going to keep going again until I see where the second function stops being a boundary and the first function starts being a boundary again. And then I'm going to go until the end where none of the functions are actually having their area considered for the total area that's being covered. All right, so I've got theta 1, theta 2, theta 3, and theta 4. Those are the 4 angles I need to consider. So the area is going to be 1/2 times the integral from my first angle to my second angle of r theta squared plus 1/2 of the integral from theta 2 to theta 3 of my outer function squared plus 1/2 of the integral from theta 3 to theta 4 of my inner function squared. Okay, so I have to calculate 3 integrals there in order to get the entire area. So let's look at an example of this. I need to find the common area between the curves r equals 1, which is that red half circle, and r equals the square root of 2 cosine 2 theta. Both of those are going from negative pi over 2 to pi over 2. So those are the only thetas I need to consider. But remember, that's not necessarily where the area starts and stops. So let's find the important angles. Theta 1 is going to be the angle where the blue function starts serving as a boundary for the area. Theta 2 is going to be where the blue function stops being the boundary and the red function takes over. Theta 3 is going to be where the red function stops being the boundary and the blue function takes over again. And then theta 4 is going to be the angle where the entire area just stops. All right. So if I calculate those, I get that theta 1 is negative pi over 4, theta 2 is negative pi over 6, theta 3 is positive pi over 6, and theta 4 is pi over 4. All right, so to figure out which of those is the boundary, I kind of need to look at the graph, and luckily I've colored in the functions in different colors. So my blue function, my root 2 cosine 2 theta, is my boundary function from theta 1 to theta 2. The red function, which is r equals 1, is the boundary from theta 2 to theta 3, and then from theta 3 to theta 4, the blue function takes over again, and that was root 2 cosine 2 theta. So now I'm ready to set up my 3 integrals. Okay, I've got 1/2 times the integral from negative pi over 4 to negative pi over 6 of my first function squared, plus 1/2 times the integral from negative pi over 6 to positive pi over 6 of my second function squared, and then back to 1/2 times the integral of pi over 6 to pi over 4 of my first function, root 2 cosine 2 theta squared. All right. So if I figure those out one at a time, the first integral evaluates to be 0.066987 and so on. The second integral ends up being 0.523599 and so on. And the last integral ends up being the same as the first, which makes sense because of how the graph looked when I shaded the areas. That was also 0.066987. So when I add all of those together, I get an answer that's about 0.658. So that is how you calculate the area between two curves, whether it's outside one curve and inside another, or whether it's the common area to both curves. So if you have any questions about this, please let me know, and I will see you tomorrow.